So this is problem number 21 from page 823. You're given a polynomial expression and you're told that x minus 1 is a factor of that, and you're asked to find the remaining factors. So since it's x minus 1, we can use synthetic division, put positive 1 on the outside, run it through with those coefficients. We do get a 0 at the end, which confirms that it is in fact a factor. And now we have this equation. It was originally an x cubed equation. Now it becomes x squared. And we have two choices. We could solve this quadratic by factoring, completing the square, or quadratic formula. Or we could go through synthetic division again. And I know that the possible rational roots are factors of 42 divided by the factors of 2. Another thing I can do is enter this equation into my graphing calculator, go to the table to look when x equals what number does y equal 0. And I saw that there was one at x equals -6. So I took -6, ran this through synthetic division. I got a 0 at the end like I was supposed to. And then I have these coefficients of +2 and +7, which means I have a factor then of 2x plus 7. This is problem number 31 from page 825. And you're given this function, this quintic. And part A says, if x minus 6 is a factor, find the depressed polynomial. In other words, we are going to use that factor with synthetic division to reduce this from a quintic, x to the 5th, down to a quartic, which would be an x to the 4th. So we'll put all these numbers across the top. And notice that we do have a nice descending order here. In other words, it's x to the 5th, x to the 4th, x to the 3rd, x to the 2nd, x, and the constant, so we don't have to leave any gaps up there. And I'll go ahead and run through this. So after taking it through synthetic division, we get these coefficients: 9x to the 4th plus 50x cubed plus 51x squared minus 150x minus 72. The nice thing is that these numbers are smaller than the original, but even better than that, the degree is 1 less. Again, the goal here is to find the depressed polynomial, so we put all those terms on there. Here's our depressed polynomial. Part B says, make a table of values for x values between -5 and +6. So you can go into your graphing calculator, come up with all of the values, probably the integer values between -5 and +6. Part C says, what conclusions can you make about the location of the other zeros? So I'll look on my table here, and I'm looking between -5 and +6. One thing I see happening is that when x is -2, y is +896, and when x is -1, y is -490. So again, I'm just looking off screen at my graphing calculator. What that means is somewhere between there is a y value of 0. So there's a 0 between -2 and -1. And if I keep going, looking in the y column, there's another sign change between when x equals -1 and x equals 0. It's going from a -490 in the y column to a +432. So anytime you see a sign change like that, you know that you're getting a 0 from that. Part D says to graph the original function to confirm your conclusions. Well, we can look at the graphing calculator and see, in fact, that there are zeros between those different locations. All right, number 9 says to find all of the zeros of the function. And what we can do here is try the rational roots theorem. In other words, look for factors of -16 that are over +1. And that trial and error process could take a long time. So because I see the leading coefficient here is 1, I'm going to go into the graphing calculator and start and enter this equation in. And I'll look at the table to look and see where there are x values that give us a y value of 0. See, there's one at +1, so +1 is going to be one of the zeros. And I'm just scrolling through there some more. I see when x is -2, that's going to be another one of the zeros. And scrolling a little bit further, I see at -8, there's another 0. So those are the 3 zeros of this function. And all I had to do is enter it into the graphing calculator and use the table for that one. This is problem number 14 on page 841. And in this one, it says to write a polynomial function of least degree with integral coefficients that have the given zeros. In other words, these are roots, or these are zeros, these are solutions of some expression. And we're supposed to write out what the polynomial looked like. So I know that this came from an x minus 3, x plus 1, x minus 1, and x minus 2. Now we have to multiply all this out, and you can multiply in any order. I see that I have an x plus 1 and x minus 1, and I know that's going to multiply to x squared minus 1. Simultaneously, I'll multiply those together. So x minus 3 times x minus 2 is x squared minus 5x plus 6. So do all the foiling and so forth. And then one more step, we're going to multiply this all the way out. That's x to the 4th minus 5x cubed plus 6x squared. And then distribute that negative 1. That's another negative x squared plus 5x minus 6. Now lastly, combining like terms, x to the 4th minus 5x cubed plus 5x squared plus 5x minus 6. So now if I were to find the zeros of this using any of the methods we've looked at, I would expect to get those 4 zeros. This is problem number 16 on the same page with the same instructions. And we're trying to write the polynomial with these zeros. So because of the x minus 4, we know we have x plus 4. And because 4 plus I is a solution, that implies that 4 minus I must also be a solution. These are called complex conjugates. Whenever you have one imaginary term in there, the complex conjugate of it will also be in there. So even though it didn't list the 4 minus I know it has to be included. So we have x minus a quantity 4 minus I and x minus a quantity, if it's plus right there, 4 minus I right here. So those aren't exactly the same. And then I do this, I'll keep that x plus 4 out front, distribute this minus sign, distribute this other minus sign, and now go to some foiling. If I'm doing this correctly, when I multiply all this out, there shouldn't be any more i's. So let's see. Distribute this x first, that's x squared minus 4x plus xi. Now I'm going to distribute the negative 4, so that's negative 4x plus 16 minus 4i. And now distribute the negative I, that's negative xi minus or plus 4i. Then negative I times I is negative I squared. Negative I squared would be like negative 1, because I squared is equal to negative 1, so it makes it a plus 1 there. And we still have the x plus 4 out front. Now going into this one, I'm expecting all the imaginaries to cancel out. So I see I have a positive xi and negative xi, a positive 4i and negative 4i, and that's all the imaginaries that are in there. So when we combine these like terms, there is a negative 8x, 16 and 1 makes 17. So there is these first two terms that we had, all multiplied out to give us this. There's still this matter of the x plus 4 out front, so now we can distribute and multiply all those terms. So I'll distribute the x cubed minus 8x squared plus 17x. Now distribute the 4, that's 4x squared minus 32x plus 68. Combine all the terms and we have x cubed minus 4x squared minus 15x plus 68. So there is the expression that has zeros of negative 4 and also 4 plus I, which means it also has the 0 for 4 minus I. This is problem number 19 from page 841. The directions say to solve each equation and state the number and type of roots. So I see it's x to the 3rd, which means that there are 3 solutions, and there could be all 3 real solutions, or we could have 1 real and 2 imaginary, but those imaginary, those complex solutions always come in pairs. So let's see what we get out of this one. Because it's equal to 0, that means we can factor it. I know that these are both perfect squares, so I'll factor it as the sum of 2 squares, x squared, and then since it's a plus here, we're going to have a minus in there, plus 1 at the end. X times 1 is x, so there it is factored. This solution is x equals negative 1, so great, we have one of those. So we have 1 real solution. And then this other one, the last part of this one is a quadratic. It won't factor, so we'll use the quadratic formula to factor that. Opposite of b plus or minus square root of b squared minus 4 times a times c all over 2a. So that's 1 plus or minus the square root of negative 3 over 2. So we're taking the square root of a negative 3, which means we have an imaginary. So we have this as our one real solution. We have also the x equals 1 plus or minus I times the square root of 3 over 2. So we have two imaginary roots. So one real, two imaginary roots, and here they are. This is problem number 35 on page 842. The directions say to find all of the zeros of each function. So the first thing I'm going to do is enter this into my calculator and look to see what zeros are showing up on the calculator. I notice that there's one at x equals 7. And as I'm looking around, I'm not seeing any other ones that jump out to me. I can look at the graph and try to figure out if there are any places where it's showing up on the graphing calculator. And that can give me another idea of where to look. So again, I'm seeing one at x equals 7. Now looking on the graph, it looks like there might be one at negative 4, so I'll scroll on the calculator until I get to negative 4. Sure enough, there is one right there. Because it's x to the 4th, I know there's 4 solutions, and I found 2. Because it's a quartic, I can't really solve that in any unique way, so we'll go to synthetic division. 1, negative 3, negative 3, negative 75, negative 700. Take all those coefficients, and then go ahead and use synthetic division. I'm going to do that with the 7. Once we've done it with the 7, then we'll do those numbers with the negative 4 after it. So I paused this, and I did the synthetic division for both of those, and we get all the way down to this. What was once an x to the 4th became an x to the 3rd is now an x squared equation. So we get 1x squared plus 0x plus 25 equals 0. The nice thing about that is it is a quadratic, and we have a lot of ways to solve quadratics. As I look at this, I see there is no term in the middle, so I'm just going to subtract 25 from both sides and then take the square root of that. Well, the square root of 25 is plus or minus 5, and because it's the square root of negative 25, that means it's imaginary. So our 4 solutions are positive 7 and negative 4. I got those off of the graphing calculator, and not a coincidence, these numbers are both factors of our last term. The rational roots theorem holds true there. And then our other 2 solutions are positive 5i and negative 5i. These imaginaries always come in pairs, the complex conjugate, so since 5i worked, it means negative 5i had to work also. This is problem number 37 on page 842. Same directions, we want to find all of the zeros. So I've entered this equation into my graphing calculator as y equals that. Then I can go to the table and look for some solutions. I see that when x equals 4, y equals 0, so that's one of the solutions. And if I don't know exactly where to look on the calculator, I could always use the graph to help out. So when I look at the graph of this one, I see that at x equals 4, it's doing that. It's not going all the way through the x-axis and continuing. It's hitting that point and coming back up. We can call that a bounce point. What that means is, since it's also this relative minimum right there, that I'm thinking I'm going to get a double solution out of this one. So let's go ahead and use synthetic division, reduce this down, and see what comes of that. So I've used synthetic division once with x equals 4, and we got a 0 at the end, which is what we were expecting. And then I'll go ahead and try 4 again. The reason why I'm trying 4 again is because of that minimum point. So let's see if it actually works twice. Sure enough, it does. So my solutions are x equals 4 twice. It must have been x minus 4 quantity squared when it was actually in the factored form. And then x to the 4th, x to the 3rd, x to the 2nd. So x to the 2nd plus 0x plus 4 equals 0. X squared equals negative 4. Take the square root, so we're getting both positive and negative 2i. So here are our 4 solutions. 4 is considered a double root, so it counts towards the 4 solutions we're expecting. Positive 2i and negative 2i are the other solutions.